So we're getting through these foundational concepts, and the whole point of today is to produce a bunch of critical issues that we need to be aware about and need to manage. The next couple of days is going to be putting those concepts into a structure that we can apply to create a known outcome each time it's applied. One of the critical factors is going to be the life cycle, and in asset management, in enterprise asset management, it's seen now as a major factor in business success. The long-term view, the wholeness of life of the business perspective is what the life cycle's about. Because if we get it wrong at the beginning, we're going to have troubles forevermore. So I want to understand what the life cycle is, see how it works, and how we can manage that and use it to our advantage to make good choices that flow throughout the operation of this business. Now, every company wants return on its investment. And when we go into business to produce a product, customers will buy and return for more business in future. So we make our profit from having a product that is of value to the client, and they come back for more, and that way we stay in business. So when we invest our money, we want to make sure we're going to get that return, and as a result of doing business, we become better off, our client becomes better off, and the whole system works for the long-term benefit of all parties concerned. So we're going to want a return on investment. To maximise that return on investment, we're going to require a couple of things. One is high productivity, and one is low operating costs, because the cost of our product is really a fairly simple equation. This unit cost of production equation, it's the cost to make it divided by the volume that we produce. And the lower that unit cost is, the more competitive we are in the marketplace. So if high productivity can produce good capacity at a low cost, then our unit cost is low, and in theory we can sell more into the market because we've got a bigger margin to work with and reduce our price and still be profitable in business. But productivity and low cost operation requires some foundational things as well, and they require high plant availability and high capacity. So you want plant that is reliable, that will work at full design rate continuously. If we can achieve that, then we'll minimise our costs and maximise our throughput. And those two depend upon another factor, which is reliability. If the plant is unreliable, I cannot get availability, nor can I get the full capacity it was designed to deliver. So reliability is, I guess, the holy grail in manufacturing businesses, making sure that we get a high return on investment. There's a lot of sense in running a business with high reliability as your focus, because it then pays back increased capacity, lower unit cost, and for a lower cost, which then is also a lower unit cost impact. Now, reliability, we know, depends on foundational concepts as well. The initial design choice is vital. If we get the wrong design choice, you put a racing car out in a paddock full of rocks, that racing car isn't going to make it. It has to be installed correctly with very low stress. Things aligned correctly, the installation with round shafts, properly clearanced bearings and natures and parts of machines. Got to operate it within the design envelope. Got to maintain it to the design requirements of the manufacturer, because they have got a limited scope to run that machine in. And what we also know, for improving success in the future, we want to improve our machines and take what we learn about using the machine into a redesign of the machine to make it even more reliable and even more robust. So reliability depends on these foundational things: the design, installation, operation, maintenance, and the learnings that we take in using that machine into the next variation, the next model, the next design. The life cycle, I can draw a simple picture of the life cycle. It's up here. It talks about the beginnings of an idea to create a business. From that idea, we talk about a feasibility. What process are we going to use? What machines we're going to use? What's it going to cost? How many people we're going to need? How big a footprint is it going to be? We go and model all that on paper, basically. Then somebody will price that feasibility design and come up with a number to invest that will produce the output we expect. We go to the banks, get the approval for the money. Then finally we go into the complete design process. And for the very first time, we begin to learn all the nitty-gritty, all the details of how to make this thing actually work. Now, if the final design, if this detailed design is actually vastly different to the feasibility, because now we know the real situation, we're in a bind because we've given a certain amount of money to do a design based upon the feasibility. This detailed design is now telling us that the original thinking is no longer suitable. And what do we do in the projects? We've got no time, we've got no money. We're then going to go looking for the shortcuts, the simple low-cost machines, the cheap manufacturers, the cheap materials of construction, because my budget is fixed. So if I get it wrong here, then I will build a plant that hasn't got the capacity to deliver the return on investment that we originally thought we were going to get. And of course, our life cycle is a series process. Same story. Get it wrong here, the knock-on effects will be there forever. Get it wrong halfway through and the engineering design is the wrong material selection, the wrong pump design for the application, the wrong machinery for that situation. I will live with that machine until it is replaced sometime in the future. So we have a series process here that I have to manage on the understanding that if I get it wrong at any point, the knock-on effect in our operation will be forever more and will last until that machine or design is replaced. And that may be 10, 15, 20 years away. So for 20 years, I'm going to live with a dog, and that dog's going to cost me a lot of money that, had I got it right back here, would have made money for me. But now it's going to lose money, and it will do forevermore. So yeah, the profits come from the operation, and if the operation has got a lot of problems because of the previous choices made, we're stuck with that. And don't want that. And I solve that by making sure that I get it right down here. So one of the techniques we apply in plant and equipment wellness is to get it right down here. I'd rather take 2 months longer in the design and get a very good, solid design that builds profit for the future forevermore than rush this thing through and save 2 months of construction and have 20 years of headaches. It just doesn't make any sense to me to do it, rush, minimise cost, and here never make the money that we could have made had we taken 2 months longer and found 10% more capital. Same story. What is done here will lead to either high failure rates or high success rates. If I want to have a successful operation, the operation's capacity to produce the right product at the right price is decided here. Make the wrong choice there, and I will forever carry that into the future of that business. So I create my failures in the future because of my bad choices at the beginning. And if I don't have a process to maximise the value of those choices, then I will, by the nature of human beings, 35% of my future failures are going to be because of the design process selections. That's been that figure for a long, long time now. There's actually been a survey done in 1978, was the first time it was done, and it's been done again a second time, probably only about, I think earlier this decade, earlier in the 2000s. And just reconfirmed what was found back in 1978. This is the future operating costs at the various stages of the life cycle of a plant. By the time we finish our planning and our feasibility, the choices we have made has locked in 65% of the future operating costs. By the time we finish the final design and select our materials and our equipment and the manufacture of that equipment, we've locked in 85% of the future costs. By the time we build it and hand it across to operations and maintenance to run the plant, 95% of that future costs of maintenance and operations unchangeable, locked in forevermore. It says to me, if I want to have low cost maintenance, low cost operation, high profitability during operation, that is the result of what happens before that phase in time. I often get low cost operation here in my choices. I get low cost maintenance here in this choice. Can't get low cost maintenance here. It's already in place. If that machine's a dog, it's a dog forevermore. And it'll cost maintenance and cost spare parts and cost breakdowns because I made a lousy choice back there. So in plant and equipment wellness, driving the right decision making back here is critical because that's where the success of the future is. The future success is chosen back there. Make the wrong choice, I can never have the success that it could have been because it cannot be achieved with what I've now got in place. So one of the techniques that we work on is to understand that there's a dividing line. After I get, once the plant's commissioned, that's it. I will never get it more successful because the success I get is built in from these early day choices. So the life cycle is the appreciation that this entire period of time, whether it's 5 years, 15 years or 25 years. These early days are the ones that matter. These are the ones where the success of the business is made. And low cost here is chosen at this stage. And once I've chosen that, then the cost is automatic. Maintenance can do little about it, operations can do little about it. And this is something that we want to control. So when it comes to our selection process back here, we need to begin feeding back to that phase particular requirements. Now, if we want to be profitable, if we want to maximise our return on investment, we're going to need a certain amount of uptime. We've got to make sure the production quality is no worse than this. Hopefully everything that is made is saleable. We want to start defining availability. How much uptime does the entire system need to produce the profit that we project is possible in this business? So we're going to feed back to our engineering guys, our finance guys, some requirements from this phase of the process. And we want to make sure that their selections and their choices will produce these outcomes. Because if I get it wrong here, I can never get what's possible. It's all too late. Now this is, we've discussed previously that human error is all around us. Business processes, depending upon the process you choose, produces a range of outcomes. Some outcomes are going to be bad, some will be good. And this is what this is basically saying. Across the life cycle between projects, designing, procurement, stores management, installation, operating the plant and then maintaining the plant, things go wrong at every single one of these processes. And this black section here with the dots is an indication that defects and errors happen all the time. And these errors flow through into operating plant because these mistakes and misunderstandings and misassumptions are in our business. Every now and again, those opportunities that they have created result in a breakdown. And some surveys were done back in the 90s on what that sort of ratio that actually is. I just want to bring this up because it's interesting to see. This was done back, I think, by DuPont, I believe, and they had a look at the frequency of failures and the way these failures arose. And this particular figure here, or these pyramids, what it's saying is, in this operation, in this plant, for every 20,000 defects, these errors, mistakes, misunderstandings, wrong selections, whatever the case is, lead to 6,500 repairs. So these defects cause us maintenance. Of these defects, 10 can lead to serious business losses, major financial costs above and beyond what we never want to see in a business. Some of those will lead eventually to possibly a death or a serious maiming of people. The whole point being is not every mistake, not every error becomes a repairable outcome. About, if this ratio is right, around about 1/3 of the errors turn into some sort of maintenance cost and some sort of maintenance outcome. My understanding is from my business, my work in industry and my work in maintenance, that I know people make mistakes. Not every mistake becomes a breakdown, but they are sitting there waiting for the opportunity to arise. So in terms of risk, these 20,000 defects, though not all will become a problem, they are always there to become a problem. And it might not be today, it might not be tomorrow, but in a year's time, these defects begin to show their evidence and become problems for us. So that human error rate table, that error rate was very, very high in maintenance, but it doesn't mean all the errors that will happen are going to become failures. Some will, about 1/3 will, but the remaining 2/3 are going to sit there forevermore, and the day might come when the other 2/3 become problems as well for us. So that's basically what this chart is saying, what this slide is saying, is that in here, errors are always happening, where they're being fed from our processes, from our people. They're residing in our businesses, just waiting for the opportunity to either become a breakdown and to be fixed, and sometimes a severe financial loss of life and of business opportunities. And that's the life cycle. Mistakes are fed in by engineers, by operators, by maintainers, by finance people, by managers, by supervisors. These are all coming in all the time from all over the place in the company, and we want to stop all that. We want to cut that right down to the least number of errors possible. So I come back to my story of Boeing. How did Boeing do that? How did Airbus do that? There's only one way to run a plane and to maintain a plane. So I don't want to have 100,000 different ways to maintain a plane. Same with the plant equipment in every other business. I can't have 100 technicians and each person maintains that pump 100 different ways, because 100 different ways will give me plenty of errors. I can't control 100 different ways to create errors. So I've got to have one way only that this machine is maintained. One way only to operate the machine. So now that one way, I can find where the mistakes are in that one way and improve that one way continuously until fewer and fewer chances of error arise. But if I have 100 ways to run a machine, I can't control 100 ways. And I'll have forever more troubles that just sit there and keep coming back year after year, decade after decade. And that's why I think we're still where we are today as we were 50 years ago. Machines that are not reliable, businesses that fail because they can't supply customers with the quality product on time they need, because the problems have never gone away. So plant and equipment wellness is about understanding where the errors can come from and building a system to prevent that, to recognise them, to protect against them, and then just have one way that, the one best way. And we're going to find the best way through our learnings and through our people's input, because I won't know it right. I'll never get it right perfectly myself, but I know as a team, as a group of guys that have different perspective on things and know different things, as a team, hey, now we can add some value on this one way, keep improving that one way. So the pyramid tells us what happens in businesses. It doesn't give us an answer, but it does indicate what we're going to start focusing on. If we reduce the number of defects, then the opportunities are not there. And in our risk equation, opportunity is part of that equation. So the fewer the opportunities, the lower the operating risk. The lower the risk, the higher the reliability will result, because there are fewer things to go wrong. And now a machine runs for longer without problems, which is improving reliability. So yes, the message here is, as I've already mentioned, we want to consider the whole life cycle. We want to not just look at maintenance at this phase, we want to look at maintenance at this phase. How can we reduce the maintenance? By selecting better machinery, better equipment from a different manufacturer, better materials of construction. If I can make good choices here and see the life cycle as a way of making money at this phase and not simply minimising my cost to go into business, then I'm looking at things in the right way. I'm looking at maximising my profit from here by making the good business choices there that bring me that outcome. So in plant and equipment wellness, we're looking across the whole life cycle because it impacts so much. And I don't want to just talk about companies at this phase of their life. By then it's all too late. All I can do now is look at the worst problems, solve those problems, and one by one improve the situation. What I can do, I guess, if I have not brought in best practice, if we're not applying good techniques, the right ways of lubrication management and reducing the stress, if I have not done that yet at this phase, then I have a way of at least improving the current situation. Can I return the machines I've got back to the full design reliability that were in there at this decision point? So if I can manage the whole life cycle, I will, because I make money by making good choices here. If it's already too late, I've got an existing plant and we are not doing yet good practice, then I know from my reliability equations that if I introduce global best practice at this phase, then I will get whatever improvement is possible to get in the constraints that I'm stuck with.
Do you know if in the aircraft industry like Boeing, is there ever an end of life for a 747, or do they just keep rebuilding? So after 20 years, everything in it major has been replaced, or ultimately does fatigue or something shut it down?
Space shuttle, is it still flying? Space shuttle is not flying because they designed fatigue life into it. They knew. Aircraft's a little bit more forgiving. They can monitor aircraft much more closer and continuously. And what's happening now with not just aircraft assets, but many, many assets in other industries, they're trying to extend the life of the asset, because to buy a new asset, buy a new plane's a lot of money. If I can get another couple of years, another 5 years out of the existing asset for a minimal cost, then that makes a lot of business sense. So with aircraft, they're now trying to extend the life. They go back and do the calculations again. With aircraft, they tend to count the number of stresses, so they know how much life is lost out of the parts because they actually monitor that stress level and realise that the degradation is happening. If there's been a low stress life, if the machine's been looked after well, it's got plenty more hours left. But if it's been flying through some nasty environments and badly treated, then they know that life is just not there. It's been taken away by the harsh life it's lived. So yeah, we can massage, we can try and work with and replace parts and extend the life, but eventually it's going to come to an end.
I heard somewhere that airplanes that make short hops have a greater degree of fatigue because the pressure and depressurization is basically fatigue stress.
Yeah. I mean, again, it comes back to as that plane's going up, the pressure's changing and coming down. So it's doing that to the body of the plane. And these are the ones that chew the life. So we count the number of, the guys count the number of flights and the duration of the flights because they know that must be reducing the life of that part of those parts. And so after so many counts of up and down cycles, rebuild or replace. Every company should think the same way. If you're a manufacturer and if you've got any machinery in your business, the machines, if they're not controlled, if you are not able to control your process nice and flat and steady, if you are causing these peaks, in time they will all fail because they have fatigued the parts. So yeah, we know what to do, we know how to manage it, we understand the situations. What we have to do now is start measuring loss of life as an automatic requirement of a business, realising that we will see the degradation developing and can then begin to either manage that and control the processes and cut those stresses down. Because if I cut stress down, I increase service life, or I just accept after so many cycles, I replace it and allow for that in my capital expense. So here, the capital budget at this point in 10 years, I'm going to buy 5 new machines. And that's been planned for 10 years ago because we know these parts won't last more than 10 years, or this machine won't last more than 10 years. So we can manage fatigue and failure, and we can actually build our businesses around replacing machines when it's time. Don't try and push your luck. When the machine's done 10 years, just go buy a new one because it's not going to go 12. It'll be very expensive because it's going to break down so often. In plant wellness, we have a technique to intentionally ask the hard questions in the design phase. So while the design is still at a drawing level, we actually say, well, look, here's the machine, here's the layout, here's the assembly drawing. What if that part fails? What's the cost of this bearing failure in the future? And we can price the cost of failure. If that bearing fails, this shaft gets damaged, I've got to buy this from Europe, it's going to cost this much to get across. We can put a cost of the consequence of failure together pretty quickly. Once we know the cost of failure, the question then becomes how often can we afford that cost? So we go in and say, well, is the cost of a failure acceptable? If the cost of a failure is acceptable, then fine. It's only going to cost $10,000 to fix. Hang on, is that direct maintenance cost or total business-wide cost? Oh, that was direct maintenance cost. So the total business-wide cost would be $100,000 based upon the knock-on effect of a breakdown. Can we afford $100,000 each time this particular part breaks? No. Okay, so now we know one failure is actually going to be too expensive. So if that one failure is too expensive, I go back to my design process and look at minimising the risks that lead to those failures. Can I design better machine, better material choice, different way of running a process? These are the questions we have to ask while it's a drawing on the table. Because once I've bought the machine, then I'm going to live with that. Then I'm stuck with a dog forevermore. Now, if the cost of failure is acceptable and one breakdown, so we can live with that. Well, how many breakdowns a year would you be willing to live with? Can you have 1 a year, 2 a year, or 1 every 10 years that you can afford? So now we answer the 2 questions. Can I afford the cost, and how often can I afford that cost? Because if that frequency is too often, we go back the same way again. Back through and optimise our design selection to maximise the profitability in future. If I've got to spend 10% more to buy a better machine that gives me 5 times less breakdowns, and the frequency of failure now is far, far less, for 10% more capital cost, I've got a business case. I can argue with the manager and say, look, you want to save $10,000? Well, it's going to cost you 4 more breakdowns. Those breakdowns are $100,000 a piece. $400,000 here, $10,000 more there. What are you going to do, Mr. Manager? What do you think we should do? So as a business case, dollars in the bank, now I can sit down face to face and say, look, I think you're wrong. You better be careful. This is where we're going to go if these situations arise. Out of this whole process, while it's a piece of paper on a table, I come up with my project decisions that are going to maximise my profit and my operating maintenance requirements that will sustain the longevity and reliability of that equipment. And all done before I even go out and lay the purchase order. Now, out of all this will be possibly extra capital cost required, but it's traded off by the additional profit I'm going to make in future. Now, will the future be as I expect today? I don't know. Now, 20 years' time, will it be what I think is going to be today? I have no idea. But today, right now, knowing what I do know, knowing how we run the business and our plant, here's the best choice we can make from what we understand now. And so I call it an optimisation loop. We're not going to have no failures. We're going to minimise the cost of our choices to the least operating cost possible. And that'll be easily done with a couple of spreadsheets and some flow diagrams and a team of guys together looking at things in the point of view, how do I maximise my operating profits in future? So yeah, we can talk about maximising profit here, way back down there and play what if risk games and what if risk modelling, and from that analysis of the cost of failures and the frequency of failures, we can make smart selections to maximise our profits in the future forevermore.